In this last video about continuity, we're going to introduce the intermediate value theorem, which is a super important result that we'll be talking about all through the rest of this semester. The intermediate value theorem I mentioned earlier is a really big deal. There are a couple of different blank value theorems, and the intermediate value theorem is probably my favorite. So this is what it says. Let's say that we have some continuous function on this closed interval from a to b. Remember, that means it's one-sided continuous at the endpoints a and b. And that we have some real number, it's a y value, L, that's going to be bounded in between the two function values. Now, I don't care which one is bigger, right? So it doesn't matter if f of a is the small one and f of b is the big one, or vice versa. L is some y value in between. If that's true, then there is guaranteed to exist some real number c in this open interval from a to b such that f of c equals L. Holy crap, what does this actually mean? All right, the written out version of the intermediate value theorem can seem really tricky, but if we just draw this thing, it's actually pretty clear what's going on. We're not going to prove the intermediate value theorem. That's something that might be best left up to analysis students or something like that. But let's say that we have some function here. We're going to say it's continuous on this closed interval from a up to b. And actually, you know what? I'm not going to draw the function first. I'm going to say that we have a closed interval from a to b. And we know that there is a function that's continuous here. We also know what these ending points are. Here they are, and maybe here's another one. We could have these switched, right? We could draw one of them down here and one of them up here. It doesn't really matter. We don't care about the ordering. Here are the y values, f of a, and down here, f of b. What we need to do now is just pick any real number L in between. Let's draw it right here. What I'm going to do is draw this y value as like a line going through here. And if our function is actually continuous on this closed interval, that means that somewhere along the way, we have to cross the line. Right there in this case. Or maybe instead, our function looks like this. And there it is. There we crossed it. Or maybe our function looks like this. And we actually cross it a whole bunch of times, right? Who knows? We're not sure. All we know is that we're guaranteed that if we go from this point to this point, we have to cross this red line. That seems like a pretty obvious result. Part of this result is that we know approximately where we cross the line. C has to be in between A and B. So we're not crossing the line out here. We could, but we're guaranteed to cross it somewhere in between A and B in this open interval. So not only do we know it crosses the line, but we have a general idea of where that happens. All right, I have a couple of examples of applications of this that I think will be helpful. So the intermediate value theorem guarantees that there is a solution to this equation on this interval from -2 to 0. Okay, let's talk about how it does it. Let's say that this here is our function, f of x. We know that this is a polynomial function, meaning it's continuous everywhere. That means x cubed minus 3x plus 1 is certainly going to be continuous on the closed interval from -2 to 0. Whoops. There. We also know that f of -2 is -8 plus 6 plus 1. That's -1. And we know that f of 0 is +1. This is an interval of y values. So we know that if we pick a number, L, in between 1 and -1, our function has to cross through that. Let's just draw this thing again. Here are our axes. Let me draw these points that we have. We have 0, 1. Oh, and look at that. I drew my axes not even close to in the right spot. -2 and -1. We'll draw it here, maybe, approximately. You can see that if we're going to connect these dots, we have to go through the x-axis somewhere in between -2 and 0. That's what the intermediate value theorem guarantees. Now, that doesn't seem very sexy or exciting, but it is a nice way of guaranteeing a solution to an equation. Maybe that's something that we care about in some further application. What I do have, though, are some more interesting applications of the intermediate value theorem. This is a fun one. The intermediate value theorem guarantees that there exists a pair of points on the Earth's surface that are opposite of each other that have the exact same temperature. That's kind of crazy. No matter what, there always is some pair of points opposite each other on the Earth's surface. What I mean is, like, if you drew a line connecting these points, it would go right through the very center of the Earth that have the exact same temperature at the exact same time. Now, it's not always the same pair of points, but there always does exist this pair of points. There's actually more to this that we could generalize with a bigger theorem, but we're only at Calc 1 right now. Let's just talk about temperature. All right, so what I'm going to do is just focus on this orange circle here. So let me draw that circle, and let me just pick 2 points on the circle, right here and here. There's a couple of cases that we have. First off, one of the cases is that they already are the same temperature, in which case, hey, congratulations, we found them, everybody. There are the points with the same temperature. More than likely, though, if we pick this pairing of points randomly, they're probably not the same temperature. So let's say that up here is hot, and up here, or down here, sorry, is cold. That means if we look at the difference from this point to this point in temperature, the difference is going to be positive, right? Hot minus cold, high temperature minus low temperature, positive difference. What we want to do now is start rotating our points around, right? So maybe I'll do them in gray here. We'll do a pairing of points right here, and then we'll rotate to this pairing of points. We're going to start moving around our circle this way. We're going to keep looking at the difference between these temperatures. What we'll notice is that eventually we're going to end up with the opposite pairing of points, where we're looking at this difference in temperatures. We rotate this around halfway around the circle. Notice that the temperature on the surface hasn't changed. It's still cold here, and it's still hot here, right? This means that our difference is now suddenly negative. Well, wait a second. Our difference function just went from positive to negative. The intermediate value theorem guarantees that that means that somewhere in this interval, there is a pairing of points where the difference is exactly 0. That's pretty crazy. So that's what the intermediate value theorem says. There is some pairing of points where this solution does exist. In this example, we probably didn't care about what this solution was, but here it makes a lot of sense to think about. If this difference function is equal to 0, that means there exists a pairing of points that have the exact same temperature. Pretty wild. Here's another example where we can do a similar kind of thing. Let's say that we're sitting at a table somewhere. We have this nice square table with 4 legs, and it's wobbly. Oh no. It rocks back and forth. Maybe one of these legs isn't really sitting on the ground. See, there's some space here, and so it's going to rock a little bit. Very frustrating. What do people do? Well, they do silly stuff, like they shove napkins under there, or they go get a different table, or they just live with the fact that they have to have this wobbly table that's going to spill anything that they put on there. Not needed. What we can do is we can fix this with the intermediate value theorem. What we're going to do is we're going to look at a function that defines the height of this specific leg. And we'll say that the height is positive because it's above the ground. We're going to force all 3 other legs to always be in contact with the ground. So that means that if this one is the one that's above the ground, these 3 we're going to lean on until we force them to be in contact with the ground. Then what we're going to do is we're going to rotate our table. And you'll notice that when we rotate it this way, if the 3x legs are still forced to be in contact with the ground, then in this situation, our table leg is above the ground, but over here, our table leg actually is going to sink through the ground, which doesn't really make a lot of sense. We'd have to pretend that the ground is some sort of like wet paper texture where we can just puncture through it super easily. But if we're going to rotate this and we're going to force all 3 other legs to be stuck to the ground, that means that this one is going to push through. That means our height goes from positive to negative. That means somewhere in this rotation, our height had to equal 0, meaning this 4th leg is going to be touching the ground. Now remember, in our setup, the other 3 legs are forced to be on the ground. And so that means that all 4 legs are on the ground nicely. No more rocking of our table. This is an actual thing that you can do. Next time you have one of these tables that rocks, just try giving it a quarter turn slowly. And what you'll find is that somewhere in that turn, all 4 legs will likely be nice and settled on the ground. Now, we have to have that height is going to differ continuously. And if you have a really jacked up ground, maybe that's not true. But as long as this height differs continuously from one point to the next, things should work pretty nicely. All right, the last example that I have is a pretty fun joke that I don't want to say it went viral because it really didn't, but it was on Math Twitter, which is fun. And here's a fun little stand-up joke by Rachel Lander about the intermediate value theorem. All right, that's one of my favorites. Hopefully that helps illuminate a little bit about where we can use the intermediate value theorem and how things work there. Again, this is a really important theorem that we're going to be using, so really make sure you can digest what this is saying. Hopefully that's helpful, and we're going to move on from continuity here.